So we've already learned about vectors. We've talked about vectors that point in space, and we've already broken vectors into components. An x component, that vector exists, is a portion of it in the x direction, and a y component, that's like the projection or the portion of it that exists in the y direction. And if the vector has three components, x, y, and z, if it's a three-dimensional vector, it'll have a z component as well, right? X component, y component, z component. But the problem is that dealing with components like that, or dealing with the pictures of the vectors, it makes it hard to add them together. We've already added these things graphically. It's very difficult to get the correct, accurate answer. And it's going to be difficult to multiply vectors as well. And we have to know how to add and subtract and multiply vectors to get into more complex topics such as work. We're going to talk about the work done on an object. We have to learn how to multiply vectors there. And also things like torque and things like magnetism and electricity. We have to know how to multiply vectors. But we can't do it by just writing components. That's too cumbersome. So the unit vectors that we learn here allows us, and here's the punchline, to write down a vector in a mathematical way that makes it easy to deal with them mathematically. And you'll understand that as we get into the problems. Now, before I can show you the glory of all of that, we need to understand what a unit vector is here. Now, a unit vector, I'm not even going to write it on the board because the definition is so simple. It is a vector, pretend this marker is a vector, that points in whatever direction it points in, that has a length of 1. So that's what the unit part means. Unit vector means a vector of length 1 unit long, in other words. So if I have a vector pointed this direction and it has a length of 1 in whatever coordinate system you're dealing with, then it's a unit vector pointed in this direction, right? If this is a vector that points this way and it has a length of 1, it is a unit vector pointed this way. If it points this way and has a length of 1, it's a unit vector pointed this way. So a unit vector literally is just a vector that has a length of 1. Any vector that has a length of 1 is called a unit vector, all right? But in order to write down vectors in a mathematically beautiful way that is nice to work with, we are going to define the special unit vectors, I call them special, but unit vectors that lie on the x-axis, the y-axis, and the z-axis, right? So here is my little model here of the x, y, and z-axis. And so this would be like the x-axis right here, and the y-axis would be coming out into the board or towards you, and the z-axis would be coming up like this, straight up and down like this. Each of these are the x, y, z coordinate system. So what we're going to do is define a unit vector that lies along the x-axis. It just means a vector that is pointed in the positive x direction on the axis, and another unit vector that lies on the y-axis, and another unit vector that lies on the z-axis. And forgive me for reusing my props here. This is from the chemistry kit from teaching chemistry, and this is really for chemical bonds, but it makes for a nice little XYZ coordinate system. So we'll put that down. Now, what we're going to do is we're going to call these, we have to have special names for the unit vector in the x direction, the unit vector in the y direction, and the unit vector in the z direction. So let's write those down and draw a picture, and it'll be very, very clear. So let's say you have a unit vector that points along the following direction, right? Let's say the x direction, and we're going to have one that points along the y direction, and we're going to have one that points along the z direction, right? Now, we have to have special names for this, because if we reuse the same letters, then we're going to get confused. So what we do is we always say the unit vector that points in the x direction is called the I unit vector, and we have this funny hat on top I'll talk about in a minute. And then we have the unit vector in the y direction we call the j unit vector, is j unit hat, or hat on the top, and z is associated with the letter k. So what you are going to have to get used to seeing is when you talk about coordinates, you talk about x, y, z coordinates. We have done that since, 3rd or 4th grade. But in vectors, you need to be thinking about I, j, k unit vectors. So x, y, z goes with I, j, k. Just say it a few times. X, y, z goes with I, j, k. Now, what are the funny symbols here? The funny symbols are, you have to have a way to write this down to remind yourself that it's a unit vector. And the funny little hat just tells you this is a unit vector. That's it. It's just a symbol that everybody understands to be unit vector. It's pretty universal, but some textbooks might have different ways to write down what the notation for the unit vectors. But this is fairly universal, I would say, in almost all books I've ever seen. Certainly when you write it on your paper, this is the way you would write it. All right, so what do we mean when we say unit vector anyway? Let's draw a picture, because a picture is always going to be superior. So let's draw a quick coordinate system right next door right here. Right here. And I'm leaving room because I'm going to draw another coordinate system over here. This is the x-axis, and this is the y-axis. Now, if I were to mark off on this x-axis, for instance, then I would say, all right, this is +1, this is +2, and +3, and so on will be up here. This is positive, 1, this is +2, and then I'll have 3, 4, 5, and so on that way. Remember, a unit vector is any vector that has a length of 1. That's actually what the actual definition is. So what we do is if we start here and we draw on top of the axis pointed in the positive x direction with a length of 1, we call this the I hat unit vector, or the I unit vector. And if we draw a vector on the y-axis up to a length of 1, physically has a length of 1, we just call this thing the j unit vector, and I'll just kind of put it right here. Now the hat just tells me that I'm talking about a vector that has a length of 1, and specifically the I unit vector, the I hat unit vector, always points in the x direction, so you never have to worry or wonder which way is it pointed. You know, because the I unit vector always points in x, and the j unit vector always points in j. Now, this is if we're working in the xy plane, but I do need to introduce what happens when you have a z component also. So we don't often in introductory physics work in the z direction because it gets kind of cumbersome, but you do need to know that there is a unit vector in the z hat direction as well. And what would that look like? So I think I left enough room, hopefully. This is the way I want you to consider that or think about that. So here, you go down here, you make almost like a typical XY plane, like this, but you don't draw the other half of it. And then from the intersection point, you draw at an angle something like this. This is supposed to represent what I showed you right here. So basically, this is supposed to represent this situation right here, where this axis is actually coming directly out of the board. It's drawn at an angle, but it actually represents coming straight out of the board towards you. That's what this one right here is representing. All right, so if this is the case, then you label this as the x-axis, this one is the y-axis, and this is the z-axis. And if you're like me, you forget which one's x, y, and z. You know z always comes up. Notice that in this representation, y comes up. The way you figure this out is when you take your right hand, you're going to learn here something called the right-hand rule, and you better get used to it because we're going to use it a lot in physics. The right-hand rule is used a lot, all the way through magnetism and electricity and other things in beyond. The right-hand rule comes up a lot. So if you have a right hand, hopefully all of you do, then some of you might not, I'm sorry. There's other ways to visualize this, but if you have a right hand, this is what you do. You take your fingers and you curl, you kind of pretend like you're cutting through the x-axis and curling into the y-axis secondarily. First cut through x, then cut through y. So you say x curled into y or x crossed into y. And when you do that, your thumb points in the z direction. This is how you figure out the situation. If you accidentally flip this thing around, like if you made, let's just take a second here. If you put this as x and this as y, then if you try to cut into x first, x curled into y or crossed into y should equal z. But see, this is pointed down. So x crossed into y is in the wrong direction as z. So this right-hand rule, it comes up a lot, and it turns out that the XYZ system that we've been using all the time is called a right-handed coordinate system. That's what it is. A right-handed coordinate system means that x crossed into y, or if you want to think of it as curled into y, it's fine, but it's really called x crossed into y. You cut into x first, then into y, thumb points to z. X crossed into y, thumb points to z. This means it has to be like this. Now, what does it mean? It means that along the x direction, which is right here, here's a number 1. Along the y direction is a number 1, and along the z direction is a number 1. That's what we have all these numbers here. And then what this means is that along the x direction, which is right here, you have a unit vector, which we call the I hat unit vector. And then along the y direction, we have another vector right here. We'll call this one the j hat unit vector. And then we have along the z direction, we have another unit vector, but we don't call it z hat, we call it k hat direction. Now you see why you have to call them I, j, and k, right? Because if we call them x, y, and z hat, it would be very confusing. Because if I wrote down x, y, and z, are you talking about the x, y, and z axis that goes to infinity in all directions? Or are you talking about the unit vector that has a length of 1 and stops after 1 unit? What are you talking about? So we have to use different letters. I goes with X, J goes with Y, K goes with Z. Get used to it. You have to memorize that. So that's why I wrote it down here. Now, in this three-dimensional representation, notice the XY plane is like in the plane of the paper here. And I'll grab my little prop here to show you. This axis is the x-axis coming to you. This axis is the y-axis, and the z-axis comes up. So the plane of the xy axis is a flat plane. What you're looking at here when we've always drawn this is like looking down. If you think about it, we just said x cross y is z. So here's x crossed with y. In this representation, z is actually coming out of the board to you. So it's more like this in this representation. So this is, when we've drawn the xy plane all these years, we've done a top-down view where z is actually coming to you, and you have x and you have y. But when we draw three-dimensional pictures, we flip it over so the x-axis comes out at you. But in all cases, x cross y gives you z. X cross y gives you z coming at you. I'm trying to take a few minutes to show you that, because if you can't get your drawings right, then you can't do your problems right. So if you draw the coordinate system with the wrong axis, then you immediately bork the problem up. You can't go any farther. So I want to make sure you understand that. All right, now I told you that these are unit vectors. They're just vectors of length 1, and they're along the coordinate system, right? Now, I do want to say here in the beginning, I want you to stick with me all the way to the end of the lesson to learn everything I'm trying to teach you, but also because I want to show you how this kind of like this unit vector business applies in situations beyond basic physics. Like it's actually used a lot in relativity theory, in gravity theory. So what happens when space-time is curved? How does that change the situation? We're not going to get into all the details, but I want to give you a little tease that this stuff is used for much more advanced things than we're using it for here. In other words, it's very important stuff. That's all I'm trying to say. All right, now we said that unit vectors were going to help us write down mathematical representation of a vector, right? So we have already talked about vector components. And we said that in the xy plane, we can have an x component and a y component. And if it has a z component, then we have a third component called the z component. So let's say that a vector called A has components. I'll say components. A sub x and a sub y. So nothing in the z direction. It's just in the xy plane. The z component is 0. Right? And then what we're going to do is we're going to do the same thing right next door. I'm going to say that some vector called B has components b sub x and b sub y. Now, we've already learned how to write these components down. Usually what we do is we just say ax equals something and ay equals something. We just write it down. But there is a way to write down the mathematical representation of the vector of the full vector using unit vectors and components in the proper way. Here's how we write it down. What we really say is that vector A, it points in some direction, right? And it has some components. What it is actually equal to mathematically is whatever the x component is, which is just a number, multiplied by the unit vector in the x direction, I hat. And then we add to that a sub y, the y component, multiplied by the unit vector that exists in the y direction. Now, I know you don't understand the full significance of this yet because you're just learning it, and everyone has to start somewhere, so it's okay. But I'm just telling you that the significance of this is really important, okay? So what we said before is that we have x and y components, but these are just numbers. Like the x component can be 3 and the y component can be 6, and that tells you where the vector points. When we write something down like this, what we're saying is that it will be 3 units in the I hat direction, which is the x direction, and 6 units, if it were 6, in the j hat direction, which is the y direction. And since this is a unit vector in the x direction, and this is a unit vector in the y direction, writing it like this sort of reconstructs what the total vector points to, because this is telling you how many vector units is pointed in the x direction, and the same in the y direction. So let me show you what I mean by that. If we draw a coordinate system right down below here, this is the x direction, this is the y direction, right? Now let's say that we have a unit vector which is pointed, you know, something like this, and the name of this vector is called the A vector. In the past, I just told you it had some magnitude and some angle, but I didn't really give you a great way to write down the whole vector, right? But we know, that, of course, that there is some angle associated with it with respect to the x-axis. And we have learned to break these vectors up into components, right? So what we say is there's an x component right here, and then we break it over here, and we say there's a y component right here. Right? And what we do is we say, well, the y component is however many units it is here, and the x component is however many units it is here. But when you think about it, the x component and the y component, a sub x and a sub y, they're just numbers. They're not vectors, right? So if I tell you the x component is 4, you know that it's on the x direction, so you know it has a direction because you know it's the x component. But writing it down mathematically, ax equals 4, it's just a number. It's a scalar quantity. These components we've been writing down are just numbers. How do we reassemble it to mathematically show that it's a vector pointed along x? Well, to do that, you have to write down that there's a component, there's a number that is multiplied by a unit vector in the x direction. Now, this is a length of 1, so when you multiply it by 3 or whatever the component is, then it stretches the vector out in the x direction, because this is a length of 1. When you multiply by a number, it makes it longer in the x direction. So what you actually get is a vector in the x direction right here, and this is called a sub x in the I direction. The unit vector I hat is just a length of 1. It like stops here, for instance, right there. But when I take I hat and that has a direction associated with it and multiply by 3, then it makes it 3 units longer. So this notation is telling you a vector that goes along the x-axis and stops right here. This is a vector. It has direction. Just writing down ax by itself is just a number. I have to multiply by a unit vector to make it an actual vector in that direction, right? And then the exact same thing happens, if I can get my bearings right, the exact same thing happens in the y direction. So the y direction has a component that goes right here. How would I write this component down? I would say it's a sub y in the j hat direction. So these are multiplied together. So if a sub y is like 6, let's say, the y component of this thing is 6 newtons or whatever it is, but I multiply by j hat. Remember, j hat is a unit vector. It's only about this tall. It's just 1 unit long. But when I take a vector and I multiply by a number, I stretch it by that. I just multiply, I keep the direction, but I just make it this many times longer. So then the vector is really this tall. So then what I say is the x component is really a vector pointed from here to here, named this. And this is really a unit vector here to here that's really named this. And the total vector is the sum of this and this. That's why I add them together. So this plus this is a unit, is a vector here. Think about if you wanted to add these together. These are just vectors, right? These are tail to tail, so you can't add them. Move it over here, so it's head to tail. So if it existed over here, how would you add them? You would connect tail to head. So the a vector literally is the vector sum of this component plus this one, which we can parallel move over here. A is the vector sum of the x vector along the x-axis and the y vector along the y-axis. But to get these vectors, it has to be a unit vector times a number that stretches it that far. Same thing here. Now, you probably won't read that in the textbook. They'll probably just write one sentence and say, this is how you write down a vector. And that's fine, because education takes time. You know, you unwrap it. It's like a present. You start using it, and then you deeper, and you're like, whoa, I guess I understand this more. It's okay. And I'm not saying I understand everything either, but I'm just telling you the things that are important because I can see I'm on a little bit of a higher mountain right now. I'm not the smartest guy in the world, but I'm a little bit of a higher mountain. I can see what this stuff is used for later, right? And so if you start viewing it the way I'm telling you to view it, that this unit vector multiplied by this makes a new vector of that length, and then adding this and this really does reconstruct it from pictorial graphical vector addition, then when you get to more advanced physics, even Einstein's theory of relativity, these unit vectors take on even more special significance. And learning what they mean in this context helps you understand more advanced applications of it. All right? Let's do the same thing for another vector. But let's just draw it in a different quadrant just so we can, do something different. So let's say we have a new coordinate system like this. This is x, this is y, and I guess I'll continue down like this. Right? And let's draw, like I said, another vector in another quadrant. Let's make this vector over here, just to put it in quadrant 3 instead of in quadrant 1, right? What would be the angle to this vector? Angles are measured with respect to the positive x-axis, so the angle is all the way over here. We still call it angle theta. It's bigger than 270 degrees, but smaller than 360 degrees, right? What's the name of this vector? This vector is named b. B vector, that's what it's called. But we know that B vector has some components associated with it. What are those components? Well, this is a projection on the x-axis, and this is a projection on the y-axis. Now, in the past, of course, we have said that it has a component b sub x, and that has a component here, b sub y. And we wrote b sub x and b sub y down and said these are the components. And that's right, but those numbers are just numbers. They don't mathematically represent a vector because b sub x equals 3 is just a number. How do we reconstruct the actual vector mathematically? We have to associate a direction with it. So what we actually say is that in this direction, in the x direction, along the axis from the origin all the way to where this thing is, this is the x component, right? How do we write the x component? We say, well, it has some number of units in the x direction, but multiplied by the I hat unit vector, because the I hat is a directional thing. It points only in the x direction with a length of 1. The I hat unit vector only points about this far. But when I take that thing and multiply by whatever this is, 5 units or whatever, then it stretches, it maintains its direction, stretches it out 5 units to make it this arrow right here. This is really the x component of the vector. Really. We were just doing a shorthand way of saying this, just the number was the component before. But remember, when you write bx and by, you know they mean x and y directions, even though we don't mathematically write it down, so it was okay in the past. How do we do the y direction? Well, there's a vector pointed down here. We call this the y component right here. How do we write it down? Well, we just say this is b sub y in the j direction. So the I hat direction points this way. The j hat direction is really just a small unit vector right here, multiplied by whatever the component is. It stretches that vector out to be the total thing. And then we say, right, let me get rid of this. Then we say that the vector b as a vector is equal to b sub x in the I direction, but then added to that b sub y in the j direction. This is how we write a vector down. They have to be added together. What you're doing is you're adding the x component vector and the y component vector. If you add it graphically, how would you do it? This is tail to tail. You would grab this, you would move it over here to make it head to tail, and it would stretch to here. How would you then, if it was like here, how would you add it? You would take the tail of this vector and connect it to the head of the other, thereby reconstructing the b vector really is the addition of this vector plus this one, the x vector in the x direction and the y vector in the y direction. Now, this is all wonderful, but we haven't used any numbers yet. It gets a lot more understandable when you actually put numbers in. So in the next couple of problems, what I'm going to do is I'm going to write down a vector in proper, we call it Cartesian notation. Cartesian because it's the xy plane. It's xy notation for a vector. But remember, we can represent a vector as in a Cartesian xy way, but we can also represent a vector in polar notation, which is a magnitude at an angle. So again, it's two different ways, and we're just mostly focused on the, in this case, the Cartesian way. So let me write down, or let me say given, I will give to you, I'll give you the following. I will tell you that there's some vector r, and r is equal to 3i plus 4j. Now this is how you're going to see vectors, oftentimes written in physics, 3i plus 4j. When you read it like this, you know it's already in xy notation, Cartesian notation, right? Now you could convert this to polar notation, magnitude and angle there. We've already learned how to do that in a past lesson, right? But for now, what we want to do is I want you to tell me what the x, the y, and the z components of this vector are, right? So that's the point of this problem. What you would write down is you would say, well, the r vector has an x component of what? Well, you say, well, this is I hat. So this is a length of 3 in the I hat direction, which is the x direction. So the component in the x direction is 3. The component in the y direction is 4. What is the component in the z direction? Well, there is no z direction. So really it's like plus, I'll just put it here, plus 0z. That's really what's here, even though it's not written there. So there's really no component in the z direction at all. This vector exists in the xy plane, and it doesn't come out of the xy plane at all. And if you want to visualize that, this is the xyz system. This vector exists in the plane down here. There is no upward direction to it as far as pointing up at all. All right, so let's draw a picture to try to recognize this or learn about it a little bit more. What we'll do is we'll draw a little xy plane, xy plane. And what we said is 3x and 4y. So we go we go 3 units in the x direction and 4 units in the y direction. I could put the tick marks, but this is 3, this is 4. And then you put your tip of your arrow right here and you say this is the vector. You see, when you write a vector down in I, J, K notation, look, I made a mistake. This is not z hat. You definitely don't write z hat. My apologies. It's k hat. Yeah, so you write I, J, K for your, and I need a little hat right there. Sorry about that. You need I, J, K. You don't put z hat. That was a total mistake. I just, you know, I make mistakes too. It happens. But what you do is you read directly off of this what the components are. You say, well, this is an x component of 3. This is a y component of 4. This is a z component. There was nothing there of 0. And so if you want to reconstruct in the xy axis, what you have is you have this right here, like this. And you know that on the x direction, if this is 3 units, there is a unit vector in the x direction. It would end about here, pointed this way, and it would be called I hat. And there's a j hat unit vector pointed up right here. But since we took 3 and multiplied, I guess I could do that. I could just kind of put it here just to kind of like for giggles. There's I hat, roughly. And here's j hat. So this is I hat, and this is j hat. These are little vectors pointed in that direction. But when I take 3 and multiply it by I hat, then it makes the full component a vector that points to here. When I take 4 and multiply by j hat, it makes a full vector that points to here for an x component and a y component that are added together to give me the vector I have. Now I showed you a picture, but I do want, with the 3D, but I do want to, you know, I do want you to get used to drawing 3-dimensional things. So what you do when you're doing a 3D thing is you make a little XY plane like this, and this one comes obliquely here. What are they labeled? X goes here, Y goes here, Z goes here. How do you know? You take X, you cross it into Y, and your thumb should point to Z, so you know you have it labeled correctly. Now what do we have here? We have an X component of 3, so we mark 1, 2, 3. That's 3 right there. A Y component of 4. 1, 2, 3, 4 right here. And there is no thing here. So how do you actually do this? What you do is you draw some dotted lines. You have to maintain the perspective. So you come down like something like this. And then from the origin, right there, you draw your vector. That's the vector that this represents. And this is supposed to represent a vector that lies in the XY plane with no Z component. It's supposed to represent this, where here is my situation. The vector is essentially pointed like this, right? It's the exact angle depends on measuring correctly 4 units and 3 units. So it's like pointed something like that, basically. And this is representing that, but it's not pointed up. If it was pointed up, you'd have a positive Z component or a K hat component. And if it was pointed down, of course, you'd have a negative Z component or a negative K hat, you know, on the vector there. All right. Let's do another one. What if I give you that I have a vector S and it's equal to -2 in the I hat direction plus 6 in the j hat direction. And I want you to tell me what the components of this vector are. Then you just read it off. You say, well, I have an I hat right here, so that means the x component, which I'm going to call S sub x, is equal to, and there's a negative here, -2. And this is the j hat component, so that means that's the y component, so that's the S sub y, and that's equal to 6. And there is no k, which means 0 times k hat, and so that means S in the z direction is 0. So these are the x and the y and the z components of this guy. And if you wanted to draw a representation of what it looked like, you would just draw a little xy plane like this. And then what you would say is it is 2 units in the negative direction for the x component. So here's -2 right here. And it is positive 6 units right here. So I'm just going to put 6 up here. That's roughly 6. And then right here is the tip of my arrow. And then I'm going to draw the vector pointed down, or not pointed down, I'm sorry, starting down and pointed up here. And so here, of course, is the angle of the vector is bigger than 90 degrees, and it's in quadrant number 2. That's basically where it is. And there is no z direction. There's no k hat. So if you wanted to draw this thing in the plane, like we did up here in terms of a 3-dimensional figure, you would do this, and you would say x, and you would say y, and you would say z. Now it's difficult to draw, you know, something like this back behind the board. It's really hard to draw. So instead, I'm just going to gesture, and I'm going to say, all right, if this is x, y, z, as I've drawn it right here, and this basically, it's in the x, y plane right here. This is x, this is y, x cross y going into z, right? And so what we have is something in the negative direction. So basically, negative x is behind the board here. So it's hard to draw because this is positive x, this is negative x. So it's still going to be in the plane down here because there is no z component, but it's going to be somewhere in the back. And so I don't, really want to spend time trying to draw it or whatever because it's not going to look clear. But you get the idea. It's still in the xy plane, but it's pointed back behind the board. If you could do a good drawing of that. All right. Now, I don't think we need to draw anymore, but I do want to do a few more. What if I give you a vector A, and I just tell you that it's 2I hat plus 3 times j hat plus 6 times k hat. And I say, tell me the components of this vector. Then you say, all right, well, I hat is here. That's the x component. So this is the x component, and it's equal to positive 2. J hat goes with y, so this is the y component, a sub y is equal to 3, and of course that's the z component, so a sub z is equal to 6, right? And I lied, I guess I am going to draw this one, because this one actually is, I don't want to say easy, but a little bit easier to draw. So this is x, y, z, if you want to draw something like that. X goes there, y goes there, z goes there. Double check yourself, x curled into y gives you a thumb in the z direction, so that's correct. So how do we draw this thing? Well, we have 2 units in the x direction. So along the x direction, that's 1, 2 units right there. In the y direction, we have 3 units. 1, 2, 3, that's right there. And in the z direction, we have 6 units. So 1, 2, 3, 4, 5, 6. How do you draw this thing? Because it's going to point out into 3-dimensional space. Here's my advice. What you do is you work in the xy plane and you kind of like draw it like this. And this kind of indicates some kind of plane. And then what you do is you go straight up from that, basically right there. So this means you're coming out and then you're going up. And this is basically, you can kind of like go like this if you want to. And what do you draw? Your tip of your vector goes right there. And I'm never going to be able to do a good job with this, but you get the idea. Something like this. That's where the vector is. And this is supposed to be indicating that it's not just pointed up, it's pointed out, away. This is what this is trying to 3-dimensionally show you. So in a 3-dimensional system, this is x, this is y, this is z. This thing is pointed up somewhere like this. That's what this is trying to show you right here, okay? Half the battle in calculus and in physics is visualizing what you're doing. If you can visualize what you do, you can actually solve a lot of problems. The trick is if you can never get into the habit of visualizing, then you can't solve anything because we all have our mental images we have to form to solve anything. All right, one more of this direction and then we'll go the reverse direction. What if I tell you that I have a b vector and here's the vector, negative I hat plus 5j hat minus 8k hat. And I ask you, tell me the 3 x, y, z components of this vector. Well, the x, the direction is here, but what is here? Negative I hat. Don't forget, this is like negative 1 times I hat. This is basically the same thing as negative 1 times I hat plus 5 times j hat minus 8k hat. So if you just see a negative sign next to a unit vector, it means negative 1 times this. So the x direction is just negative 1, and this is, of course, in the x direction. So the x component is negative 1, right? The y component goes with whatever j says, which is 5, and the z component is whatever k says. There's a negative sign here, so it's negative 8. And these are the x, y, z components there. So here, what I've done is I've given you the x, y, z representation of the vector with the unit vectors, and we write down the components. So you can learn how to read this and understand what it means. Next thing I want to do is I want to go the other way. I want to give you a drawing in the xy plane of some vector, and then we have to together, or you have to write down the vector representation in terms of unit vectors. You have to write the vector down, in other words. We're going to go backwards. So for the first problem, let me draw what it is we need to talk about. So here is the first situation. Here's x, here's y. All right, and what I have here is 1, 2, and I have 1, 2, 3, 4, 5, 6, 7. This is 7. And basically, I have a vector which goes right here. Something like that. And this vector is called C vector, right? So how do we write this vector down? Well, what you say is you say C vector is equal to whatever the component is in the x direction. It's 7 units in the x direction, But what we have to do is write it as 7 times I hat. Remember, the I hat unit vector is just a vector that stretches to the number 1 position. When we take that unit vector and multiply it 7-fold, we're stretching that vector out 7 times longer. So the x component is really a vector that stretches from here all the way to here. That's what 7i means. But then we add to that whatever's happening in the y direction. 2 times j hat. Remember, the j hat unit vector is just stretching to here, to a length of 1. We multiply by 2, it makes it a vector this long, and this plus this gives us the vector like this. Now, there is no k component because this is drawn in the xy plane, and that would be like looking, basically it'd be like looking down, if you want to think about it, x, y, and z coming out of the board, and there is no z component at all. So if you wanted to, you could put 0 times k hat, but nobody ever does that. You just leave it blank, and you know that the z direction is 0. All right, let's move along to the next one. We only have 2 more of these things. Let's draw the next one. Here we have, this one's a little tricky for me to draw, but I'll try my best. Try my best. Okay, so here's x, there's y. Now, let's go 5 units to the left. 1, 2, 3, 4, 5. That's -5 units to the left. Then we have -1, -2, -3. That's -3 units down. So the intersection point of those 2 will be right here. And this means a vector is going to point from the origin down to here, like this. So what is the Cartesian vector representation of this? And this is called vector D. I guess I'll call it D vector. So D vector is going to be written as the x component, but the x component is -5 units. You got to put the negative that points to the left. So it's -5 times the unit vector in the x direction, which is I hat, right? And then you have to add to that, you have a -3 right here in the j hat direction, which is the y direction, right? But we never write it as plus and negatives. What we really do is we say -5 in the I hat direction minus 3 in the j hat direction. This is what you actually will circle on your exam or your test or whatever. This is -5 units along the x direction. Remember, the I hat direction points in the positive x direction, so when you multiply by -5, it flips it around and stretches it 5 units this way. The j hat direction actually points up, so when you multiply by -3, it flips it around and stretches it 3 units. So that's the component, and that's the component. That's the representation. You add those together. All right, now I lied a little bit. I thought that one was going to be the one that was going to be tricky to write down. Actually, it's this last one. And this is the last one in this lesson here. So what I'm going to do is I'm going to draw this. I'm going to draw a try to draw a three-dimensional representation. Here's x, and then here's y, and then here's z. And if you forget, just take your x, curl it into the y, cross it into the y, and your thumb should point in the positive z direction. All right, so how do I draw this? Well, I'm going to draw 1, 2, 3, 4 units this way. 1, 2, 3, 4 units this way. And I want to represent something not in quadrant 1. I want to bring it below. So what I'm going to have to do is I'm going to have to extend. This is the positive z direction. I'm going to have to extend the negative z direction down here, right? And how many units do I want to go down below? I think it was 6. So 1, there's 2, there's 3, there's 4, there's 5, there's 6. How do I, so that's -6 down here. How do I represent this thing? It's tricky, I'm not going to lie. So what I'm going to do is I'm going to take this guy here, make a little parallelogram that tries to represent the perspective of what's happening. And then I'm going to go down towards the z value, which is right here, and I'm going to say that's the tip of my vector. And I'm going to draw the tip of that from the origin straight down here. Is it perfect? No, but what it's trying to illustrate, I'll just show you, is this situation. So here's x, here's y, here's z, and this vector is pointed down below, something like this. The x and y component are still positive here. This is positive x and positive y, but this would be positive z, but this is pointed down, something like this. So that's what that's attempting to illustrate. All right, so I'm going to put that back. And what is the vector here? We're going to call this vector E. Let's call it E vector. So what is the E vector? All you do is you say, well, what's the x component? It's 4 units in the x direction, so that's the I hat direction. In the y direction, it's also 4 units. So it's 4 units in the, we got to write it as the j hat direction. In the z direction, it's -6 units, but we don't write it as plus and negative. We just write it as -6 in the k hat direction. So 4i plus 4j minus 6k. This is a vector pointed this way, a vector pointed this way, and a vector pointed this way. We add all three of them together. If you arrange them all head to tail and then drew the arrow, like we did graphically, from the tail of the first one to the head of the last one, you would arrive at this vector. That's why adding them all together gives you the vector you're seeking. Now that's actually it for the lesson, but I do want to talk about one more thing. I'm going to put my paper down to talk about it. This whole concept of unit vectors extends way beyond this kind of basic physics representation. Now this is not an advanced class where we're going into crazy detail about advanced gravity theory or whatever, but I do want to tell you, to give you motivation as to why this kind of thing is useful beyond this level of stuff. So in this situation, pretend this is our x, y, z coordinate system. So this x coming out at you, or I should say, yeah, like this. X coming out at you, curled into y, gives me a positive z direction. So x is coming at you. And then we have y, and then we have z, positives, right? Now, what we basically say is that everywhere we solve physics problems, this XYZ system is the same. If I start an experiment over here where I'm firing a cannonball and I have a XYZ system, then it's fired from the origin, the XYZ system is here. And I do my little experiment, the cannon is fired, and I measure everything. Now, if I instead choose to fire the cannon over here, I have the exact same system. Right? If I'm over here in this part of the universe, and if I'm over here in this part of the universe, the XYZ orientation remains the same. X is coming to you, then we have Y, then we have Z, right? In general, they're basically, no matter where I do my experiment, I just translate the coordinate system around and do my experiment. But the modern theories of gravity, which are not totally complete, to be honest with you, but they are the best that we have right now, they are basically geometric theories that say that space and time around us, gravity is a manifestation of a curvature of space and time. What curves space and time? Well, it turns out that massive bodies and also energy and also pressure is what actually curves space and time. Now, we actually can't see space and time. We move through space and time. So it's hard for us to manifest or to see when space and time is curved because we don't see space. We just move through it. We don't actually see an object that we call space. We just know that we can move from point A to point B. So how would we ever know if space and time were curved? How would we ever know that if we don't actually see time? We just experience it. Well, we see it because what we call a curving of space and time, or what we know is a curving of space and time, we see it because that is what gravity is. We feel gravity, and that is something that we think of massive bodies attracting other massive bodies, but really it's a manifestation of a curving of space and time. So if space and time were flat, meaning no curvature, we use exactly the same coordinate system everywhere because nothing is curved. But what if space and time were curved? What if we have a black hole or a star, and this is not a perfect analogy because this is not exactly the same situation, but it's the same sort of thing. Comparing this board as being a flat board and comparing it to this sphere has a curvature in a higher dimensional space than the board does, right? If I do an experiment on the top here of this curved sphere, then I do my experiment. But then as I move around this sphere to do more experiments in different parts of the universe, my entire coordinate system changes. These coordinates, x, y, and z, have unit vectors that point in the different directions, I hat, j hat, k hat. And in all of Physics 1 and Physics 2 and Physics 3, you basically just treat that as a coordinate system that can be moved, but it's just moved around. It has the same orientation. But if we are in a curved space, then the coordinate system is different in relative because it's a curved space. Locally, if you're an ant on the surface of this thing, it might look like it's still, everything's the same. But as a global perspective, the x, y, z, or I, j, k unit vectors are all pointing in different directions. And they can move with respect to one another, but they may not even be perpendicular to each other in the same way that they are here. And so, why am I telling you all this stuff? It's because when you get into higher level math, there is mathematical ways to change the I, J, K unit vectors due to whatever situation you're in. Maybe high gravity, maybe high energy, maybe you're moving at the speed of light or near the speed of light or whatever. The coordinate system itself might change, is what I'm trying to say. Now, in the past, in algebra and in basic calculus, we just draw x, y, z and say that's the coordinate system. But now you're learning about vectors and that there's really a unit vector in the x direction and the y direction and the z direction. And those unit vectors really define the directions of the coordinate system. And as you go into a high gravity field, which is a curvature of space and time, this thing might change orientation and they might actually change angle, like there may not be 90-degree angles between them anymore if space itself is curved enough. And so a lot of the complexity of Einstein's theory is because it's not just the law that's changed, it's the entire coordinate system that's changed and warped and makes it much, much harder to deal with, near a black hole. But I guess I just wanted to make the connection that these ijk unit vectors, we call them basis vectors in higher level math. These basis vectors, these ijk unit vectors, we call them basis vectors. They form a coordinate system. And the coordinate system can change and become more complicated if you're near a black hole, for instance. And so what you're learning here has applications far beyond these basic ideas. I like to try to tell you these things when I can, because I don't want you to look at this and say, okay, I can solve some cannonball problems, yay. I want you to think, oh, well, maybe I should remember this because Jason said I might use it 15 years from now when I'm studying something really cutting edge. You might be the next person to discover the next best thing or the next big thing or the new formulation for how this stuff works. And so I want to give you the motivation to know to hang on to some of these things, maybe for 15 or 20 years when you get to that point and you're discovering the next big thing. All right, that's the end of this lesson. Unit vectors, very important. I'd like you to take it from the top, play it again, solve these problems yourself, and get used to the idea of writing down a vector in ijk notation, because going forward, we're going to see it a lot in physics. Learn anything at mathandscience.com.